Hey everybody, Chris McClure here. Now we are going to move on into the second section of chapter 3 today with discussion of graphing a function. And folks, this is a pretty easy discussion because we know what a function is. We know that a function is a relation between two sets of numbers such that for each number in the domain, that number, each number gets assigned to one, not two or more, but just one element in the range. Now, there could be some number or any number of numbers in the range that are assignments to multiple numbers in the domain, but you can't have it where one number in the domain gets assigned to two or more numbers in the range. Okay, so now what we're going to look at is graphing functions. We know how to graph functions. All right, you graph equations, right? We've already had a couple discussions on graphing already. So this is really an extension of the two topics of graphing and functions. So we're going to go through this fairly quickly unless you have any questions. Now, if you have any questions, feel free to email me, all right? Also, this discussion's in the textbook in more detail. All right, so moving along here. Well, here's an example of a function. It's not in the form of an equation, but what we see here is price of gas as a function of time. In this time, or in this case, it's going to be years. And here we have inflation adjusted price for gas. Since 1980. And we could actually plot this. We would normally make more sense by looking at the graph compared to looking at the table of numbers, because we humans, at least for most of us, are visual creatures. So we can kind of get a sense for the trend in this case right here. This is a graph of this function right here. They say that a picture says 1,000 words, so it's really true. On the horizontal axis, we've got year. On the vertical axis, we've got price in terms of dollars per gallon. And this shows the ups and downs of the prices, and of course you can kind of see where the prices are relatively low in the late 90s and early 2000s compared to what they were in the early 80s as well as in the mid to late 2000s. How did we graph this? Well, each of these black points comes from each of these ordered pairs. So you want to plot 1980, 3.41. Well, here's 1980 right here on the horizontal, and we're understanding price to be functions, or the function, or a function of time. So that's why time, in this case years, is on the horizontal. And on the vertical, we have the price. And boom, there is 3.41 cents. And so forth. Luckily, we have computers now that could do the hard work. But we could do this by pencil and paper if we really wanted to. We know what a graph is, right? And we know what a function is. But how do we know that we're looking at the graph of a function? The short answer is the vertical line test. The vertical line test is basically where, if you have a vertical line that hits the graph anywhere at two or more points, then that graph is not the graph of a function. So, for example, here we got y equals x squared, and here's the graph of y equals x squared. And nowhere would you have a vertical line that intersects the graph any more than once. And same thing for y equals x cubed. Both graphs pass the vertical line test. And so their corresponding equations indicate that y is a function of x for both of those equations. All right, so both of those are functions. But here are two examples of non-functions, because there are plenty of places, plenty of values for x where the vertical line intersects the graph at least twice, both for this graph and for the circle here. And indeed, both of these equations are not functions where you have y would be a function of x. That's not the case. Y is not a function of x. Now you could say that x is a function of y, but that's not really what we're talking about here. When we talk about functions, we'll usually understand y to be a function of x. I know some people have already emailed me that question, and I just want to make it clear that unless otherwise specified, we would think about y as the potential dependent variable and x as the potential independent variable. So when we see an equation and involving x and y, the question is whether y is a function of x or not. All right, moving along here. So both of those are not functions, because neither one of them pass the vertical line test. So let's talk about obtaining information from or about the graph of a function. So suppose that this graph is all you have to define your function. And of course, you've got the coordinates and some points on the graph. Can you answer the question, what is f of 0? Meaning, what is the function's value when x is 0? Well, when x is 0, the function has the value of 4. Okay? So f of 0 is 4. And we could also answer the same question for what is f of 3 pi over 2? Well, here's x of x is equal to 3 pi over 2, so f of 3 pi over 2 is 0. And f of 3 pi is negative 4. What is the domain of this function? Well, it looks like the graph starts here and ends there. So x varies from 0 to 4 pi. So that would be the domain, 0 to 4 pi, which you could write either in this format or this format. Understand also that we are including x equals 0 and x equals 4 pi, so that's why we have this closed interval like you see here. What is the range of the function? So I'll look at the minimum value and the maximum value of the function. Minimum is negative 4, max is 4. So from negative 4 to positive 4, that would be the range of this function. And all real numbers in between. How about the intercepts? Are there any intercepts? Well, the y-intercept is going to be 0, 4. And then x-intercepts are this one here, the pi over 2, 0, 3 pi over 2, 0, 5 pi over 2, 0, and 7 pi over 2, 0. So those are the 4 x-intercepts that I see. So here are 5 intercepts. Okay, what about when the function is equal to 2? What are the x values for when the function is equal to 2? That's really the same thing as asking, where does the line y equals 2 intersect the graph? Well, I don't know that we can get the exact x values, but we know that the line y equals 2, that purple line that just appeared, intersects the graph right there, 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 and there. So if we could find out the corresponding x coordinates there, 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 and there, then we would have the x values for which the function is equal to 2. And it's going to happen 4 times. For what values of x does f of x equals -4? Well, I see f is equal to -4 right there and right there. So pi and 3 pi over 2. Pi and 3 pi. Did I say 3 pi over 2? I meant 3 pi. So pi and 3 pi. For what values is the function positive? Well, take a look right here. So as long as x is greater than or equal to 0 but less than pi over 2, the function is positive. And also when x is greater than 3 pi over 2 but less than 5 pi over 2, and also when x is greater than 7 pi over 2, you'll have the function being positive. So you can go ahead and write the union of those 3 intervals. Make sure that you include 0 and make sure that you include 4 pi. But you're not going to include 3 pi over 2 and 5 pi over 2, nor would you include pi over 2 and 7 pi over 2, because at those 4 values, this one, this one, this one, this one, f is equal to 0. So f would not be greater than 0 at those 4 values. All right, moving along here. Now, suppose that we've got this function right here. F of x is equal to x over x plus 1. And I've got this question for you. Is the point 1 comma 1/2 on the graph of this function? And folks, this is easy to find out. All you need to do is just evaluate the function at x equals 1. What is f of 1? Well, you plug in 1 for x, you get 1 over 1 plus 1, which is 1 over 2. So indeed, the y-coordinate would be 1/2 on the graph when x is equal to 1. So yes, that point would be on the graph. What about it when x is 2? If x is 2, just plug in 2 into the expression. 2 over 2 plus 1, that's 2/3. So 2 comma 2/3 would also be a point on the graph. Now, on the other hand, we could ask, well, where is the function equal to 2? If f is equal to 2, what is the corresponding value for x? Well, folks, just replace the function value by 2 and solve for x. So replace f by 2 and then solve for x. So do a little bit of algebra, maybe multiply both sides of the equation by x plus 1, multiply that left-hand side out, subtract 2, subtract x from both sides, and you get x equals -2. So -2 comma 2 is yet another point on the graph of this function. So here's a function right here, 0.56 times x squared minus 34.39x plus 1,212.57 plus 20,000 over x. And this function, which we're calling C over bar, is the average cost of the manufacturing X computers per day is given by this function. Now, when we talk about the average cost, it's not uncommon for us to use this over bar. Okay? So what would be the average cost when we have 30 computers? Well, X is the number of computers, right? So replace X by 30. Replace X by 40, replace X by 50 to compute the corresponding average cost. We could even plot this graph. Well, we probably wouldn't manufacture 0 computers or a negative number of computers, and maybe 80 computers would be the maximum that we're at least interested in looking at. And we could also create a table and maybe even answer the question, what is the X value that minimizes the average cost? Well, look, if we are going to manufacture 30 computers a day, what is the average cost? Folks, just plug 30 in for X. So you're going to have 30 squared, which is 900, times 0.56, minus 34.39 times 30 plus 1212.57 plus 20,000 over 30, whatever that is. And I showed you last time how to evaluate functions. So you could evaluate this function on your calculator at x equals 30, at x equals 40, at x equals 50. The smallest cost being for these quantities of computers, 1232.97. Suppose that we're wanting to actually minimize our costs. What is the number of computers that we would need to manufacture, in order to minimize costs? So we can go ahead and plot that function. Well, let me go ahead and do that. Pull up my graphing calculator here. Fire up my calculator. Go to the equation editor. I'm going to clear out y sub 2 and clear out y sub 3. And then go back up here to y sub 1 and clear that out and put in 0.56 times x. Let's try it again. 0.56 times x squared minus 34.39 minus 34.39 times x, and then plus 1212.57 and then plus 20,000 divided by x. Now, we're going to let x go from 0, from 0 to 80, as the instructions told us. Then let the scaling go for every 10 units. So every tick mark will be 10. Now, how do you determine what's a good scale? Well, what you could do is you could take the max minus the min and divide by 10, and then maybe round up. So 80 minus 0 is 80, divided by 10 is 8. So maybe 10 would be a good scaling factor, right? Y minimum, maybe, I don't know. Let's call it 1,000 maybe. Y maximum, maybe 1,400. With tick marks every maybe 40 or 50. Let's go with 40 maybe. And let's see if we can hit the graph function. Wow. Maybe we need to go back to the viewing window and set the Y max to maybe 2,000. Maybe set the Y scale to 60 or something. So anyway, so there's a pretty good view of this cost function, average cost function. And we could see that the minimum is going to happen somewhere around here. And if you want, you can hit the trace button. And you could see when x is 40 that it's pretty close to the minimum value, 41, 42. So you can keep on hitting your left arrow and then maybe your right arrow to kind of go back and forth to see if you can minimize this cost. So it kind of looks like it bottoms out when you have about 41 or so computers per day being manufactured. Do you remember our list? Let's go, or our table, I should say. Let's go to our table and let's set it up. We can start off at 0 and go by ones, delta table being 1 as well. And then we can go over to the table menu after we get out of the table setup menu. And we could just scroll on down and keep an eye on the cost over here in this column, in the Y1 column, and look to see for where that minimum cost is. See where it bottoms out. So we understand that it's somewhere close to 40. So if we're at 40, it's 1233. At 41, it's 1231.7. And then we start going back up after that. So I would say that 41 computers per day would be what we would need to manufacture in order to minimize cost. Okay? And that's pretty much what's showing us in this right here. These little screenshots. Okay? So that's pretty much it for our discussion of the graph of a function. And we see what the graph is. The graph is nothing more than a collection of points, x comma y, which satisfy the equation. And we would know whether or not the graph represents a function depending on whether or not the graph satisfies the vertical line test, which basically says that if a vertical line hits the graph more than once anywhere, then that equation is not that of a function. Okay, and that's pretty much it. Okay, so we'll see you next time. Have a good weekend. Right now it's Saturday, June 22nd. I took yesterday off. Friday, I developed a bug, and I wasn't feeling well, and I took the afternoon and evening off, and feeling a lot better now. Not 100% perfect, but took some medicine, got out, got some exercise, and ate some good food. And a couple more days, I should be 100% again. All right, so we'll hope everyone's doing fine out there. I appreciate everyone's comments, and everyone's doing fine on the homework, as far as I could tell, except maybe for 1 or 2 people. And but folks, if you have any problems with anything and you have any questions, please send me an email, and I'll try to get back to you within a short amount of time. It might take me a couple hours, but I will get back to you. All right. So we'll talk with you later. Take care. Good luck. And I'll try to post another video tomorrow, Sunday, June 22nd. Actually, June 23rd, I mean. Tomorrow, June 23rd. All right. So take care, folks. Talk with you later. Bye.